Okay, in this session we're going to talk a little bit more about the integral. From last time we introduced the integral, and I do want to be clear we were specifically talking about definite integrals. And what do I mean by a definite integral? Basically, as long as your integral has limits of integration, it's a definite integral. We will get a little bit later on into talking about integrals without limits of integration, and we call those indefinite integrals. But for now, we're going to focus on definite integrals. Now, you might recall a couple of sessions ago, I went through how to find the area under a curved shape and talk a little bit about what that means. And we spoke specifically about y equals x squared. This is a smaller version of the graph that I drew in that. Not on any particular scale. Y equals x squared. And I had asked you to, well, first we worked out the very specific result between 0 and 1. That area, as you might recall, worked out to 1/3 square units. In our language of integrals, we would say that from 0 to 1, x squared dx worked out to be 1/3. And then I asked you to generalize this, to take it up to a very general x instead of 1. And had you worked that through, you would have found that the integral from 0 to x of x squared dx worked out to be 1/3 x cubed. Now, what you might notice here is that 1/3 x cubed is the antiderivative of x squared. And that is a generalization that always holds. What I'm introducing here is something sometimes referred to as the fundamental rule of calculus, and that is the following. The integral from a to b of f of x dx, assuming that f of x is continuous on the interval, ends up being the antiderivative of x evaluated between b and a. From our earlier notation, you'll note that for a function lowercase f of x, its antiderivative is given by capital F of x. And here I am evaluating it between the limits b and a given in the integral. This thing is a bit of a big deal. The fundamental theorem of calculus. And it's a very small portion of the fundamental theorem of calculus, but it's introduced within there. And it's what's let us analytically work out the value for integrals over certain areas, for definite integrals. And I'm going to work in a couple of examples of that. In fact, I'll do a quick example right now. This one is not out of your textbook, it's one I'm just making up. So let's see, I was interested in the area between 0 and 2 of x squared. Now I could rationalize this. If I end up doubling the space underneath the curve, since it's going up by x squared, my height should go up by 2 squared or 4, so my overall area should be 4 times 2 times bigger than the original, or 8/3. Let's see if this holds out. So I work out the antiderivative of x squared, which will be 1/3 x cubed. This line is often shown to say that I'm evaluating it between 1 and 2. So what that would work out like is 1/3 of 2 cubed minus 1/3 of 0 cubed. And this is me evaluating the antiderivative between the limits of integration. The second part is just going to go to 0. The first part is 8 times 1/3, or 8/3. And that would be the area between x squared and the x-axis, and between x values of 0 and 2. Okay. One thing you may have noted is that when I stated my antiderivative, I didn't put a constant of integration on there. I didn't put a plus c. And since that constant would be the same in each case, when I do this subtraction, that constant of integration would cancel out. So when you're using your antiderivative on a definite integral, you don't need the constant of integration there, the antiderivative constant stuck on the end. All right. I will do one or two more examples with this, but I want to mention a few rules of working with definite integrals. These rules are laid out on page 289 of your text, but I'm also going to do a couple of examples along the way. And so again, this is following along the rules for definite integrals. From page 289 of your text. And I'll just dive right in. Keeping in mind as we do this, it's helpful to think that these integrals represent area between a curve and the x-axis. So the first rule they state, order of integration. So order matters, and based on what we just stated for finding the value of a definite integral using the antiderivatives, reversing the order of integration will reverse the sign of the result. So if instead of going from b to a of f of x dx, I go from a to b, I end up reversing the sign. So if I go off that last example that I just had, we know that the integral from 0 to 2 of x squared dx will work out to 8/3. From that, I could say the integral from 2 to 0 of x squared dx would work out to negative 8/3, based on that first rule. The second, and if we were in class where we're having a back and forth, I would take a moment and ask people what they thought this would work out to, if my lower and upper limits of integration are the same number. And if you think about that from an area perspective, the area taken up between a and a, it has to be 0. You're actually not giving any width to the area that you're looking at. So it doesn't really matter what the function is. If your upper and lower limits of integration are the same, then your area ends up being 0. There's not really an example to give with that, just what happens. I might go over here for number 3. 3 is sometimes referred to as a constant multiple rule. So if I have some constant times f of x dx that I'm integrating, and I should point out here someplace along the way that k is a constant. K is a constant. Just like with the derivatives, the constant multiple just stays a constant multiple throughout the whole thing. So this would be the same as if I had k outside my integration. And just end up integrating the function. Ooh, cut off a little bit there. From our earlier example, let's say I had 3 times integral from 0 to 2 of x squared dx. This is going to end up being 3 times 3 or 8/3 or 8, but that would be exactly the same result as if I had brought the 3 inside the integral. I apologize for how messy this is. And if I went back, the antiderivative of 3x squared would just be x cubed. And if I evaluate that between 0 and 2, I would just end up with 2 cubed minus 0 cubed, or 8, the same result as I had before. Four is called the sum and difference rule. So if I've got two functions that I've combined through addition or subtraction, the end result will be the same as if I figured out the integrals separately and added and subtracted the results. Sounds relatively self-explanatory. I probably want to end up doing an example for that. 5, additivity. So if I figure out the area between A and B under f of x, and then I add to that the area between B and C under f of x, shouldn't that be the same then as the area between A and C of f of x dx? So for example, I know the area between 0 and 2 . Let's say I also want the area between 2 and 5. That should end up being the area, same as the area between 0 and 5 of x squared dx. Which, if you then wanted to move on and evaluate, the antiderivative of x squared is a third x cubed. I evaluated between 0 and 5 means I'd have a third of 5 cubed minus plus a third of 0 cubed, or 125 over 3. There are two more rules they mention here, although I'm not going to spend much time on those. Rule 6, the maximum inequality, basically gives upper and lower limits to how big an integral can be. If you take the lowest value of your function, multiply it across its domain, the value of your integral can't be any lower than that. If you take the maximum value of your function, multiply it across the domain, then your integral can't be any bigger than that. Effectively, in that multiplication, you're making a small area and a big area, both that are rectangles, that the integral's got to be somewhere in between. And domination is really just saying that if one function is bigger than another on an entire domain, then its integral will be bigger than it on the entire domain. Again, those are number 6 and 7 in that list. I'm not going to spend a whole lot of time talking about them. Okay, a couple of other statements that get thrown out here. Pardon me while I shift. So, apparently I accidentally stopped recording and didn't realize it and finished off the rest of the session and didn't record it. So, I'm just going to pick off from where it cut off, although I had everything written out, so I'm just going to sort of reveal and go along. The next thing that I was going to talk about was the average value of a function, which I show here. This is similar to when we talked about the average rate of change of a function, but you'll notice instead of working off of the function itself, we're working off the integral of the function. And this is giving you the average value of a function, the average value for f of x over an entire domain, as opposed to the average rate of change. From there, we can move on to talk about the mean value theorem, which looks an awful lot like the average value of a function. And the mean value theorem for a definite integral basically states that there's going to be some point on your function that is equal to the average value of the function. And we'll work with an example or two of this in a minute. And now some examples dealing with everything that we've talked about to this point. The first example is example 1 from page 290. And on that we are given some pieces of definite information. We're told we've got two functions, f of x and h of x. And we know the value of the integrals of those functions over very specific domains. We don't know the functions themselves. We don't know what they are. We don't really care what they are. We know what the values of their integrals are, and that's what we'll work with. So first out, we're asked to find the integral between 4 and 1 of f of x dx. Now I know the integral from 1 to 4 of f of x dx is negative 2, so if I reverse the order of integration by the rules we mentioned before, then I reverse the sign of the result. So if this integral is negative 2, the opposite order of integration would make that positive 2. The b part asks us for negative 1 to 4 of f of x dx, and since I know the value from negative 1 to 1 and the value from 1 to 4, I can just put those together to get the value from negative 1 to 4. Putting those together, I'd have 5 plus negative 2, or 3 overall. The c part, where we've got multiples of both functions involved, but in each case the integral is over negative 1 to 1, so I can just combine them as shown here. 2 of the f of x dx results, that'd be 2 5s. 3 of the h of x dx results would be 3 7s, and I'd have 2 5s plus 3 7s, which is 31. The last part of the example, d, e, and f, are all ones where we don't have enough information to work it out. And in that case, for the d part, we've got a 0 involved in our limit, and none of these have a 0 as either end of my limit. So I do not have enough information to work out this integral, because I don't know what the functions are, and I don't have any result mirroring this. E kind of looks like you should be able to do something. This limit is from negative 2 to 2, and our original is from negative 1 to 1, but we really can't. Since I don't know anything that's going on outside of negative 1 to 1, based on this integral, I can't assume that it's just double or anything like that, because I don't necessarily know what's happening on the range outside these values. So I do not have enough information to state what this integral's value will be based on this. And lastly, in f, if it were just f of x here, I'd have enough to work with. Negative 1 to 4 would incorporate both of these integrals, and I can work it out. But I've only got from negative 1 to 1 on h of x. I don't have anything from 1 to 4, so I don't have enough information to do this part, which means I don't have enough information to do the whole thing. Two more examples of working with these. Pardon my low-tech solutions. Example 3 on page 291 asks you to find the average value of this function on the domain from 0 to 3. So I've got my formula, but in order to work it out, I'm going to need to figure out this integral. And that's what I do over here. The integral from 0 to 3 of 4 minus x squared dx. To work that out, I'm going to need the antiderivative of 4 minus x squared. The antiderivative of 4 would be 4x. The antiderivative of x squared would be a third x cubed. And I need to evaluate that between 0 and 3. So I have my expression of 3 filled in. I subtract my expression with 0 filled in. The zeros are obviously going to make everything over here 0. So I have 4 times 3 is 12, minus a third of 3 cubed, which is 9, or 12 minus 9, which is 3. Coming back to working out the average value, I end up with 1/3 times 3, which works out to 1. A second part of that example asks us to find where this function satisfies the mean value theorem. In other words, where does my function equal the average value of the function? By the mean value theorem, it has to happen someplace. So I set 4 minus x squared equal to 1. I get x values of plus or minus root 3, but inside the domain I'm interested in, only the positive value of root 3 works. So that ends up being my solution there. The last example is example 4 from page 294, where I'm asked to evaluate the integral from 0 to pi of sine x dx. The antiderivative of sine x is negative cos x, and I evaluate that between my limits of integration. So I end up with the negative cosine of pi minus the negative cosine of 0. Always be careful with your signs, it's easy to get lost in them. So cosine of pi is negative 1. The negative of negative 1 is 1. And I subtract the negative cosine of 0. Cosine of 0 is 1. Negative 1 is negative 1. And 1 minus negative 1 is 2. So my overall integral works out to equal 2. which I can also say is the area then between the line y equals sine x and the x-axis between 0 and pi. I apologize if that second part was a bit rushed. Apparently when I've gone through it once, I tend to go through it quicker the second time around. Anyway, that is all I have for this session. There'll be some questions to go along with this on the Google Classroom site. And thanks for your time, everybody.